Welcome back, students. Now in this lecture, you'll learn mapping of logical address to physical address in case of paging as well as segmentation. Then we'll also learn about virtual memory, the issues related with virtual memory, demand segmentation. Now, just look at this diagram. We have 16-bit logical address given to us. Out of 16-bit, 6-bit is reserved for page number and 10-bit offset we have. Now the given logical address composed of this 6-bit page number, it indicates page number 1, and the offset is indicated by this binary combination here. Now trying to look at this address in the page table, we get to know about which frame is being occupied by this page number 1 in the page table, process page table. So we found an entry here, and this is actually the memory address onto which we will be combining the 10-bit offset in order to form 16-bit physical address in case of paging. I hope you have understood this. See here, page number is 1, its 6-bit combination is given as this, and it has got 10-bit offset. So looking at the page number in the process page table, the address frame address we are getting here is 000110. So this means the particular page number occupies this frame address. So we will take this and we will combine it with the 10-bit offset. So this will give us 16-bit physical address. This is how mapping of logical address to physical address is done in paging. Now let us see how this can be mapped in segmentation. Here also we have 16-bit logical address, out of which 4 bits are reserved. 4 bits are reserved for segment number, and here we have 12-bit offset. So looking at the process segment table, we will find that segment number, and then here the process segment table has got some extra information, that is the length of the segment and the starting address of the segment, which is indicated by base information. So process segment table constitutes 2 types of information: length of the segment and starting address of the segment. So here if we look at this logical address, the 4-bit segment number indicates segment number 1. So we'll find the entry in the process segment table. We got its length and then the starting address, which we will combine it together with the 12-bit offset in order to form 16-bit physical address in case of segmentation. Hope you have understood this concept. Let us discuss about memory, virtual memory. What do we mean by virtual memory? It is a technique which allows the execution of processes which are not completely available in memory. This means that by virtual memory technique, we can allow the execution of certain processes which may not be residing completely in the main memory. But even though it seems to be like it is there in the memory. So the main visible advantage of this virtual memory is that the programs which are larger in size than the physical memory can also be loaded into the memory for their execution, assuming that we have a big size of main memory. So it gives us a feel that we do not fall in shortage of main memory. at any time. Now, virtual memory is the separation of user logical memory from physical memory. So here virtual memory will give us a separation of logical memory from the virtual memory. And this separation allows an extremely large virtual memory to be provided for programmers when only a smaller physical memory is available. See, when a programmer is writing a program, the program it may exceed the size of the main memory. Okay, so but we do not put any burden over the programmer to think of that it has less amount of memory. So we give it a feel that we have a big size of memory available to us. Now, in situations where entire program is not required to be loaded in the main memory, then users written error handling routines are used only when an error occurs in the data or computation. There may be situations where you do not need to load entire program in the main memory. One such case is error handling routine, where the error handling routines are brought into the memory for computation only when an error occurs. Then at certain options and features of a program may be used rarely. It may happen that the programs that are written by the programmers, it has got certain features which are very rarely used. So they need not be brought into the memory all the time. Whenever required, we can bring that particular block of code into the memory. Now, many of the tables are assigned a fixed amount of address space, even though only a small amount of table is actually used. So here is a situation where we do not need to load the complete table, where only a small amount of table is being used actually. Now, the ability to execute a program that is only partially in memory would counter many benefits. We will have many benefits when we adopt this strategy. We will call the part of the program which is required at the time of execution only. This will save our space, right? Even though we will be facing load and store operations frequently, less number of input output would be needed to load or swap each user program into the memory. Here we have a program would no longer be constrained by the amount of physical memory that is available. This means that we can load larger programs that are quite larger than the available physical memory we have. So each user program could take less physical memory and more programs could be run the same time with a corresponding increase in CPU utilization as well as throughput. Here, if we adopt this strategy, that only bringing the part of the program which will be executed further, then this will save the memory space, and eventually the program will occupy less space. If program occupies less space, more of the programs we can load into the memory and they can be run at the same time. This will eventually increase the CPU utilization and throughput, which is the main objective of introduction of virtual memory here. Now, virtual memory is commonly implemented by demand paging. Here we have another technique to implement virtual memory, that is demand paging. This can also be implemented in segmentation system. Here we will be using, in case we are using segmentation, then it will be demand segmentation. Look at the word demand here. Demand paging. Only those pages will be brought in which will be demanded. Okay. And only those segments will of the program will be brought in, which are required, which are demanded here. Let us have a look at this diagram to better clear our concept of demand pages. Now here we have a virtual memory onto which we have some pages loaded. Suppose we have page 0, page 1 till page n are there in the virtual memory. Now actually page 2, when we try to map in the memory, we try to find the entry in memory map, we get the entry here. Here we have an extra information, a memory map we are keeping with us that will show us the entry of a page in virtual memory, and finally which will be occupying an address into the physical memory. Okay, now this will be placed, this will be assigned a physical memory here, and when it is not required, then that can be loaded to the packing store. When it is needed, it will be brought in again to the physical memory. Now we'll look at the demand paging mechanism. Now this is a system that is quite similar to paging system with swapping. Swapping, changing, interchanging. When we want to execute a process, we swapped it into the memory. Whenever we want to execute a process, when a process is executed by the processor, the basic first primary requirement is that it needs to be there in the main memory. The processor will read instructions from the main memory. Then rather than swapping the entire process into memory, however, we use a lazy swapper called pager. In case of demand paging, this swapping the entire process, swapping in, bringing in the entire process into the memory, we make use of a swapper called as pager. When a process is to be swapped in, the pager guesses which pages will be used before the process is swapped out again. Now here we put a responsibility on the pager to make a guess of which pages of this process will be used further for its execution. Then instead of swapping in a whole process, the pager brings only those necessary pages into the memory, and thus it avoids reading into memory pages that will not be used in any way, decreasing the swap time and the amount of physical memory needed. So here the pager will make a guess and will bring in only those pages that are required. It will not bring the pages which will not be used in any way. So this will decrease the swap time as well as the amount of physical memory which will be needed. Now the hardware support that is required for demand paging distinguish between those pages that are in memory and those pages that are on the hard disk using a valid invalid bit scheme. Here we require an additional hardware support to make a distinction between those pages that are in memory and the pages that are on the hard disk. So here we will be having a scheme called as bit scheme. We'll mark valid and invalid to all the pages. Valid and invalid pages can be checked by checking the bits. Marking a page will have no effect if the process never attempts to access the page. So it will not have any other effect if we are not the process if it doesn't attempt to access the page, then there will be no effect, while the process that executes and accesses pages that are in memory resident, execution proceeds normally. So here when the process executes and access the pages that are already in memory, there will be no problem. The process will execute normally. So valid bit is for pages that are in memory. Invalid bit is used to mark those pages that are on the hard disk. Now here we have a diagram to illustrate the same thing. Here we have a program A and these many pages are there for program A. 4 pages are there. We have program B which includes 3 pages. These are in main memory. So when we swap out program A, it is swapped out of the main memory and it is kept on the backing store. As you can see here, these pages, they occupy the location over the hard disk. And when we swap in a program B, it occupies the space in main memory. So when it is demanded, only those pages are brought in. Rest of the pages, they are not brought in and hence they are marked as invalid. Now if an attempt is made to access a page having invalid bit, will cause a page fault trap. This means that we are trying to access a page which is not loaded in the main memory and hence it will cause page fault trap. So it is actually a result of operating system's failure to bring the desired page into the memory. But page fault can be handled here. We can handle page fault by making a request to the page to bring into the main memory. See here how it can be done. Now operating system, it loads a program is loaded. Now here certain pages required a reference to a page is made which is not in the memory. Okay, so then it falls into a trap. To come out of the trap, operating system will make a request to load this particular page from the backing store and it is loaded into the physical memory. Okay, fine. And an entry is being made into the page table that it occupies certain frame location. Okay, I hope you have got this concept. Now here is a stepwise description of demand paging. Step 1 is to check an internal table for this process to determine whether the reference was valid or it was invalid memory access. I hope you have understood what do we mean by valid and invalid memory access. Valid memory access will be those if we are making a reference to the page that are loaded in the main memory. Invalid memory access will be a reference to those pages which are not in the main memory but they are on the backing store. Step 2 is if the reference was invalid, then terminate the process. And if it was for a valid page but page have not yet brought in, then we need to bring into that particular page. Step 3 is find a free frame. Since we are loading the page, we need to find a free frame that will be allocated to the page. Step 4, schedule a disk operation to read the desired page into the newly allocated frame. Step 3 is when the disk read is complete, modify the internal table kept with the process and the page table to indicate that the page is now in the memory. Step 6 is the last step. Here we restart the instruction that was interrupted by illegal address trap. And this process can now access the page as though it had always been in memory. Hence, the operating system reads the desired page into the memory and restart the process as though the page had always been in the memory. That's it for today. See you in the next lecture.